Well, that's no fun. Thank you. Kylie, I'm sorry, I didn't see that before. Oh, I was just on mute for like way too long. That's depressing. Sorry. Um, yeah, chat me again if I'm muted before. Okay. Yeah, sorry. We're looking at selection sort. I think all the binary search stuff we already did before, so we didn't miss a whole lot. But for selection sort, right? So for n items here, we're going to go look at every other n minus k, which is, when we average it out with our math, it's still n squared, right? As u2, n minus 1, n minus 2, n minus 3, on and on and on. So for the index to check, we'll see if we find a smaller value. So if my sum list at the index to check is less than the smallest value, right? Then I have a new smallest value. Oh, actually, this should be, sorry, this is the smallest value index. We just need the index here because we need to swap later. So we'll look at my sum list at the smallest value index. Then my smallest value index is equal to the index to check. But I need to know where I'm swapping from into my current index. So if the current index is the smallest, no swap happens, that's fine. But then if I find a smaller number, I need that index to do the swapping from current index to smallest index to swap those around. So we'll go find the smallest value somewhere in here. When we're done with that inner loop, then we swap. Right? So I can say my temp is my sum list at the current index, and then my sum list at the current index will equal my sum list at the smallest value index, and then my sum list at the smallest value index equals the temp value. Right? So save off what was here, replace it with the smallest thing, replace the smallest thing with what I had. And again, you can do this in one line in Python, but I always hate that. It confuses me. So doing it in 3 lines makes a little more sense. And we just keep doing this until we get to the length of -2. Oh, if we're less than, actually, okay, so length -1 is the last index. I think just -1, because it'll stop when it's, so if the length is 5 here, because we have 5 values, this will stop at 4. No, it'll stop at 3. 3 will be the last index, so that's correct, because 5 is the length, 5 minus 1 is 4, 3 is less than 4, 4 is not less than 4. And we need to make sure this, I guess we could do that in a for loop as well. We could for range, for current index in range, length of sum list -1. There we go. That way we don't have to do our own increasing here. Yeah. All right, so we should be able to selection sort out a list. So if we put this in a different order, and now the reason why the best performance is still O of n, or n squared, is even if this is the smallest, I still have to go look at all the other small ones, right? It's just, there's no good here. So let's give it a list number in range. Let's do 10. Let's get sum list to sort. So list, we'll take our sum list to sort. We'll append random int 1 to 100. And then we'll print the sum list to sort. And then we'll sort it. We'll call our selection sort, given my sum list to sort, and then we'll print our sum list to sort again. So we can actually sort it out here. So we get some random numbers, 1 to 100, and now we get sorted numbers, 1 to 100. Okay, so our 60, 74, 33. I think it's sorted. So we did our own sort. Now this is terrible performance, right? So average is O of n squared. And still best is, usually we don't care about best, but it's sad that even in the best case, it's still really slow. All right, so that's the selection sort. So we're selecting the smallest value and swapping it in. The other common sort here we're going to look at is our insertion sort. given some list. Now, insertion sort behaves a little bit differently in that we still have a sorted portion and an unsorted portion. But what we're going to do, so let's take those original numbers. We had 7, 2, 5, and 9. So with the selection sort, we said let's start at the beginning and go to the end minus 1. With the insertion sort, we're going to say start at 1 here and go to the end. And for the insertion sort, what it's going to do is insert it into the sorted portion here. So we still have a sorted portion and an unsorted portion. So at this point, all of the numbers in the sorted portion are in sorted order. Now, there's only one number there. But sure, it's in sorted order because there's just one number. So the insertion sort will insert the value into the sorted portion in the correct position. So what it's going to do is going to do a bunch of swaps. So if it's if it's smaller than the number before it, it swaps. And it keeps on swapping until it's no longer less than the number there. So 2 will swap with 7. We'll have 2 and 7. And then it's done. We got to the beginning. There's nothing greater than, nothing less than it. No, nothing greater than it that comes before. So now our sorted portion is 2 and 7. And then we have the 5 and the 9. So then we get to the 5 and we say, okay, are you less than the value before you? You are, so swap. So now we have a 5 here and a 7 here, and 5 says, are you less than the thing before you? No, it's done. So my insertion stops. We put it in the correct position, and now my sorted group is size 3, 2, 5, 7, and I look at the 9. And we say, okay, now I have to sort this one. Are you less than the thing before you? No. All right, we're done. We just stop, and now our sorted portion is all of it. So the best case here, if you give it a list that's already sorted, it just has to look at all the values and say, yep, you're good. Because it's no swapping, no moving has to happen. The worst possible performance of this is n squared if you're in a reverse sorted list. If you're a 9, a 7, a 5, and a 2, the 7 has to swap, the 5 has to swap and swap, the 2 has to swap and swap and swap. So you get every item swaps n minus 1 or n minus k back, and you get an n squared performance. So the worst case is n squared. On average, again, it's still n squared because it's just sort of, if some of them have to swap n minus k, but some of them don't, we average it out. It still gets to be n squared. Hector, my friend, thanks for donating to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. I'm glad I'm not on mute, so you can hear me say that. So our loop then is still sort of a double loop, but it behaves a little differently. So we're going to say for my current index in range, we're going to go from 1 to the length of my sum list here. So from 1 to the end. Now we're going to loop again until we either get back to the first index, to index 0, or we're no longer less than. So two pieces happen here. So we're going to say while my current index is, if we're greater than 0, and my current index, the sum list of current index is less than my sum list of current index minus 1. So as long as we're not at 0 and we're less than the thing that comes before me. If we're less than the thing that comes before me, we need to swap. So we have temp is my sum list at my current index, and then my sum list at my current index. We'll put the sum list at the current index minus 1, and then my sum list at the current index minus 1 equals the temp. We'll swap. After we swap, we'll take current index minus 1. Right? If we're greater than 0 and we're less than, we swap. So if when current index is 1, it might swap with position 0. Right? Because we're going to start at 1 here. So current index starts at 1. It's greater than 0, yes. If the item at current index is less than the thing that comes before it at 0, let's swap them. That's why we're going to just decrease it ourselves here. You could do this with a for loop and then break it. I like the while loop because then we can have our condition here. Like these two things are true. Either way could work. So If we're always greater than the thing that comes before us, because we're in sorted order, this never happens. No swapping ever takes place, right? We just look at for current index from 1 to length and just do those comparisons. So we should be able to do the same insertion sort here. Let's do the insertion sort on some list. See what we get. Make sure we get sorted order. So 20, 23, 27, 31, 40, 42, 49, 62, 80, 94. Looks like we're in sorted order. So we're successfully able to do an insertion sort. All right. So all of this was based on comparing greater than or less than. Right. And you can sort in reverse order if you just flop your less thans with your greater thans. Right. But that's a little trickier. So like you can sort things descended, or you could sort it and then reverse it. It's probably an easy way to do that. We got options for how we want to do our sorts, but those are two basic sorts that we look at. And then we looked at how we find values. Again, just finding a value is really slow because you have to look at all of them. But if it's sorted, you can do your binary search. I like the recursive approach. It's more efficient to do it without recursion, but again, that sort of hurts my head sometimes. So I think this is pretty straightforward to do the recursive bit here. And we've talked about recursion before, so hopefully that makes sense. Some more spaces, spaces, spaces. Okay, I get my yellow lines to go away. So another really cool way of sorting that some really smart person came up with. This one kind of hurts my head, but you can do a radix sort, which is, I think, my favorite one. And the sorts here that we looked at are comparison sorts. You have to compare the values. On average, the best comparison sort is n log n. That's the best we can do when we sort. But there are also methods of comparing here that don't compare, which kind of hurt my head the first time I thought about it. So you never look at, is this value less than this value? There's never a comparison between values here. So the radix sort has a couple different options here on how we do these things. You can get into the specific details later, but I just think this is the most fascinating sort. It's essentially a bucket sort. So what we're going to do is we're going to sort some values. So let's work with the same. Let's do 3-digit numbers. So let me do a new page here. So shout out a bunch of different 3-digit numbers. We're just going to throw them in a list for a minute. You just need like maybe 7 of them. 101. And they can be less than 3 digits as well, but no bigger than 3 digits. Okay, so 94, 732, 580. Give me like 2 more. 50, 420. All right. So if we want to sort these values without ever comparing them, what we're going to do is, now this does rely on us knowing something specific about these values, is that they're all 3 digits or less. So you can't radix sort everything necessarily. So in this case, what we're going to do is we're going to make buckets. So I'm going to make a bucket here for 0 hundreds. I'm going to make a bucket here for 100 numbers. I'm going to make a bucket here for 200 numbers. I'm going to make a bucket here for 300 numbers. And on and on and on and on. We make a bunch of buckets based on the leading digit. And then I'm going to make more buckets here. I'll make buckets based on the tens value. A bucket with a 20 in the tens place, right? And a 30. And a 40. And on and on and on and on and on. I need a 0. I forgot my 0. 0 in the tens place here. And then we do another set of buckets for the ones place. 0 ones, 1 1, 2 ones, 3 ones, and so on and so on and so on and so on. So as we look at each value here, we put it in the appropriate bucket. So 580 goes into has a 500 value here. So we get 580 in here. And then it's in the 80s bucket as well for 580. And then it's in the 0 bucket here as well. 580. So I put it in each bucket at each level for each of its digits here. And then the 101, right? So we'll put 101 in here, 101 over here, and 101 over here. And we did that with all of the numbers. 94, right, is in here. It has no hundreds. It has 9 tens, and it has 4 ones. And so on and so on and so on. So what we do is we go to the first bucket and we say, okay, what's in here? And then we start looking at, okay, let's find the numbers that are in that bucket and in this bucket. Okay, now let's find the numbers that are in this bucket and this bucket and take them out of this bucket. That must be the smallest one. Numbers in this bucket is the next smallest. Numbers in this bucket are the next smallest, and the next smallest, and the next smallest, and the next smallest. So without ever comparing them to another value, we just put them into these buckets and then pull them back out in the right order. So crazy way to sort things. So you can do this with letters, numbers. Other values don't work very well for radix sorts, though, depending on what we're trying to sort. Like if you want to write a custom class, you can't really bucket. What do we have, like an account class? How would I bucket my account class? It's kind of so it doesn't lend itself well to all things. But if we're dealing with integers, and this is sort of this idea with integer keys, you can get really cool performance. So n plus r is your performance here. What is r is the range of numbers to be sorted, right? Keys of size k, digit size d. Some really interesting stuff you can do with these. And the larger values have a bigger k because it's a bigger range. So for sorting numbers like 1 to a billion, that's a real big range of numbers, but number of digits, we only have, 10 digits to sort with billion, right? I think it's 10 digits. So it gets interesting. So, and you can look more at this in your algorithms analysis class as you continue on. But just the idea that you can sort things without ever comparing them blew my mind when I learned about it. So I think that was really fun. All right, so let's take a look. What else do we have here in the chapter we need to look at? Sorting and selection. Yeah, so we're not going to get into merge sort. This one's really cool, but it's a more complex sort. The idea that you can divide and conquer. And merge sort is great if you can take the work and spread it across multiple processes and do it in parallel. It's the idea of multi-threading. So generally our computers do one thing at a time. Right? We have one processor, but the processor might have multi-threads. So you can do more than one task on the processor at once. It gets a little bit crazy, but this is also great for distributed work. If I can take a piece of work and distribute it across lots of servers in a network, they can all do a small piece here and it gets done faster. So divide and conquer is a great strategy for that. Quick sort, usually really good, but can perform really slow. Again, probably a little more advanced than we need to get into right now. Comparing the sorts, our built-in sort. So we don't actually, not have the, they must have been earlier in one of these chapters then when we did sorts. When did we do those other sorts? I don't even remember when we did those. Do you remember when that was? We do like a selection and an insertion sort. Can we just search the book? There we go. PDFs are amazing. Is it not in here? Insertion sort. Okay. Oh, insertion sort is. That is in chapter 5. What was this? Array-based sequences. Okay, so we might have talked about the insertion sort back then, back in chapter 5. And I hate his notation. This like J equals K, while J like A of. Why don't you use better names? I don't know. Maybe one day I'll write a textbook and then I can really complain about people. That's okay. All right. That's about it for sorting and selection. I want to talk a little bit more about the final project. And again, I think I said we're going to have time at the end of every session. We're not going to take the whole class period for all these topics. Next week we'll do our lab on sorting and selection, and then we'll talk about ethics on April 4th. Have some time to work. I don't think we'll need 4.6 to talk about ethics. We will do an ethics lab on 4.11 though, but it shouldn't take up the whole amount of time. And then we just have final project work time on the menu from there. Hi, can I help you?
There's a legacy lecture provided by Dr. Scott today in a large lecture hall.
The large hall is probably down that hallway, and then to the left, there's that's where the large auditorium is.
Okay.
That's my guess. I don't know for sure. Sorry. Have you heard about that one? Okay. I'm not on the mailing list for a lot of things. So, all right. So for our final project, right, we looked at a couple things, talked about some ideas here for Texas Hold'em. I want to talk a little bit about class design, because if we build it with classes, it's going to make your life a lot easier here. Let's see if I can find it. I think we talked a little bit about some classes, but not a whole lot of details here. So the idea of a Hold'em hand or a Texas Hold'em hand, right, is kind of a noun. And what attributes does it have? Well, it has its 2 cards, right, and then it also has the 5 shared cards, or knows about the 5 shared cards, or any way we want it to handle dealing with that. But really, the noun of a Texas Hold'em hand is your 2 cards and 5 shared cards. You don't always have the 5 shared cards, right? Sometimes you have no shared cards, right? At the first round, at the second round, you have 3 shared cards. In the next round, you have 4 shared cards. In the next round, you have 5 shared cards. So that shared card list will vary. Here as we go, but you've got your 2 cards, right? And then we know about some shared cards or not, whatever we have there. Kind of makes up that noun, right? As we do these odds and things, we need to generate possible. This is a 5-card shared hand, or the 5 shared cards available, right? And the very first time here, there's a lot of different, 2 million different ways you can have 5 cards out of 50. That's a lot. We're not going to do all of them. That's where this Monte Carlo analysis will come into play. But as we look at this, we're going to fill out a full 2-card hand with 5 shared cards. Once you have that, you can calculate your best possible poker hand. This idea with a poker hand, that's its own noun as well. A poker hand is just 5 cards, a 5-card poker hand. And 5-card poker hands, we should be able to compare ourselves to another 5-card poker hand. Right? Are we less than, are we greater than, are we equal to? So I can take a poker hand, compare it to another poker hand, and see, is it better than, worse than, or ties? Right? Greater than, less than, or equal to. So if we have the poker hand class that takes 5 cards and figure out how to make it compare itself to another 5-card poker hand, part of that work is done. Then what we get to do with the Hold'em hand, right? We said each possible Hold'em hand has, I don't even know if I wrote this down, has 21 possible 5-card hands you can make, right? Because 7 combination 5. If we take our 7 cards, my 2 plus the 5 shared, in combination 5 at a time, there's 21 possible hands. So I'll go through all 21 of those and find the best possible poker hand for a given Hold'em hand. So there might be a function in the Hold'em hand class that says, get the best possible poker hand. Its job is to go find the 21 possible hands, figure out which one is best, and it can return that to you. Then to see, does one Hold'em hand beat another Hold'em hand? You get this Hold'em hand's best possible poker hand and this Hold'em hand's best possible poker hand, and see if it's greater than, less than, or equal to. So like all of it hinges on poker hand, 5-card poker hands being comparable, to find your best hand with a Hold'em hand, find the other best hand, opponent's best hand with the Hold'em hand, and see what do we win, lose, or draw to see if we won the bet or not. So as we build it out here, those like 2 classes become very core to using it. And then the other thing we're going to generate is odds, right? Display the odds of winning. So of all of the possible hands my opponent could have here, how many times do I win, how many times do I lose, and how many times do I draw, divided by the total number of hands they could have, tells me my chance of winning. Right? So you used to say, hey, you have a 75% chance of winning because 75 out of 100, like right, whatever the actual math worked out to be, possible hand my opponent could have. So we know there's at least 990 possible opponent hands when we know all the cards on the table. So out of those 990, right, if I have a 75% chance of winning, that means, nope, where's my decimal place? 0.75, there we go. 742 times I won, or so, right, as we're generating these odds. I can say, okay, I looked at all 990 hands my opponent could have. 75% of the time, I would win. Sometimes I would lose, sometimes I would draw, and that's how we generate those odds. So if we have a function in Hold'em hand to say get odds of winning that returns a decimal value, right? We can display the odds of winning to the player, and the computer can use that same function, get odds of winning, from the computer's hand perspective, right? The computer's hand, the function works identically. Here's the hold'em hand. What possible hands could the opponent have? The opponent's the player this time versus the player looking at the computer as the opponent. It's one hold'em hand. It knows some shared cards. Whether or not we need to do the Monte Carlo analysis and not do all 2 billion combinations, right? Because that would just take way too long for us. And we don't have a database we can go look up, so we'll just do some basic analysis. And like even fractions of 1% here are fine for now, because as you're running it and testing and playing with it, make it fast. Like as you think you've got it correct, and then you can start increasing this. Like I think 1%, 2 million should be still pretty slow, because that is for those 2 million still looking up 21 possible best poker hands, right? Even if we've narrowed it down to 2 million possible hold'em hands and 5-card shared combinations, it gets a little funky here as we're doing that. So again, start small. It's perfectly fine, right? We want to increase that number as we go to get a little better analysis. So whatever your computer can handle. If it takes more than 2 or 3 seconds, trim it down, right? That's okay. You don't need to be sitting there for 30 seconds while it just computes. Okay, that sort of idea. So as we build out our classes, the hold'em hand class and the poker hand class, they work together. If poker hand can compare itself to another poker hand, then hold'em hand can find its best possible hand. Hold'em hand can find its odds of winning, doing the Monte Carlo analysis based on what shared cards it knows about. It can just generate a bunch of different possibilities. Hey, here's a bunch of different 5-card hands. For each of those 5-card hands, here's the bunch of opponent hands it could have. However, we want to trim that out and see what we want to come through. So that's the gameplay piece, the actual working piece here. Again, we've got about 4 weeks or so to get this done, right? I think our final presentation date is April 25th. Ideally, you're done by the 18th, right? I would love to have this done so you have no stress for finals week for this class. You got enough stress for other stuff going on. If you need the time, you got an extra week, right? Feel free to take it, but hopefully the rest of this month we'll have some time, in class. We'll have some in-class work time to get this thing knocked out. Here is sort of the goal, where I can be around and answer questions. Okay, does that make sense for kind of talking about how we might design this? Now, that's not the only way. There's definitely other ways you can approach it, but I think this way makes sense and is easy enough to tackle in terms of I can build a poker hand class that compares itself to another poker hand. Is it less than, is it greater than, or is it equal to? Then I can build up the hold'em hand, find your best possible poker hand of the 21 possible hands, 7 combination 5, that sort of thing. Okay, it's a lot to tackle. It's a big project. That's why we've got a month to work on it here. And this idea of 10 commits at least over these 4 weeks is like, let's do a little bit at a time. You don't have to have all the features working. Forget the odds. Leave the odds to the end, right? Get a poker hand working, and then get a hold'em hand working, and then get a round of betting working, and then add multiple rounds of betting, right? You can build it in slow pieces here, so we can test it out and play with it as we go. Is sort of the idea. Okay. Questions, thoughts, concerns? If not, we got the next 20 minutes or so to work on this. Or go get some coffee or something. I definitely need some more coffee. I am out. I'm sad. All right, awesome. Sorry, folks were remote. You pester me if I didn't see the chat here. Sorry, I was on mute, but I don't think you missed too much there at the beginning, so should be okay. Thanks, everybody.